Organization chart. This organization chart shows the project team structure. Asriwinda Livia Wahidin is the project leader, Nona Nabila Natasha is the secretary and design creator, Amira Ilyana is the information collector, and Nurhan Sadra is the expert engineer.
Wastewater is water that has been contaminated by human activities such as domestic use, industrial processes, and agriculture. Although it is mostly water, it contains harmful pollutants and pathogens that can threaten public health and the environment if not treated properly. Wastewater treatment is important because it prevents the spread of waterborne disease, protects aquatic ecosystem from pollution, and supports sustainable water management. Today, wastewater is no longer seen only as waste, but also as a valuable resource that can be reused and recovered. A wastewater treatment plant, or WWTP, is designed to remove contaminant from wastewater. The treatment process includes primary treatment, which removes solid waste physically, and secondary treatment, which uses microorganisms to break down organic pollutant. This project focuses on Taman Kubang Krian, which has experienced rapid urbanization due to the presence of the University Science Malaysia Health Campus and Hospital University Science Malaysia. The increasing population has led to higher wastewater generation, while the existing sewerage system is no longer sufficient. Therefore, the development of a modern and sustainable wastewater treatment plant is necessary to protect public health and preserves the surrounding environment.
Our project focuses on achieving two primary objectives to ensure environmental safety and engineering accuracy. First, we aim to design a wastewater treatment plant for Taman Kubang Krian that fulfills Malaysian regulatory standards. This is achieved through a comprehensive two-stage process utilizing primary treatment for physical removal and biological secondary stage to reduce organic matter and nutrients. Second, we are committed to delivering high-quality engineering work. This includes preparing detailed Excel sheet for all design calculations, such as flow rates and tank sizing, as well as professional AutoCAD drawing to establish the plant final layout and physical dimension.
Problem statement. Rapid development in the Taman Kubang Krian area has significantly increased the amount of domestic wastewater generated from residential, institutional, and commercial activities. However, the existing sewerage system was not designed to handle this increased wastewater flow. As a result, untreated or partly treated wastewater may be discharged into the environment, which can cause serious environmental pollution. Pollutants such as suspended solid, organic matter, and harmful microorganisms can degrade water quality and pose risk to public health. If this issue is not properly addressed, it may affect surrounding water bodies and living conditions. Therefore, a properly designed wastewater treatment plant is proposed to treat domestic wastewater up to the secondary treatment level and ensure compliance with mentioned standard and guidelines.
In this project, a systematic approach was adopted to design a domestic wastewater treatment plant. Overall, the methodology is divided into two main components, namely the project workflow methodology and the wastewater treatment process methodology, which cover all stages from the planning phase to the development of the final treatment plant design. So for project workflow methodology, the project workflow begins with a design briefing and planning stage, which aims to identify the project objectives, scope, and design requirements. This is followed by site selection and data collection, where relevant information such as wastewater flow rate, population equivalent, and design criteria are obtained. Based on the collected data, the problem statement is defined and suitable unit operations are proposed. Preliminary design calculations are then carried out for each treatment unit before selecting the most appropriate treatment method. Finally, the design is finalized and the preparation of the report and project presentation is complete. So for the wastewater treatment process methodology, the system begins with the sewer system, where raw wastewater from residential and commercial area is conveyed to the treatment plant. Due to elevation differences and the need for a stable flow, a pump station is used to transfer wastewater to subsequent treatment units when gravity flow is insufficient. The wastewater then passes through the screening unit, which serves as the first primary treatment process to remove large solid materials such as plastic, cloth, and wood debris, thereby preventing damage to downstream treatment equipment. After screening, the wastewater enters the grid chamber where heavy inorganic materials such as sand and gravel are removed, while oil and grease are separated to protect the following treatment unit. The wastewater is subsequently directed to a balancing tank which functions to equalize flow rate and pollutant concentration, ensuring more stable operating conditions for downstream process. The wastewater then flows into the primary sedimentation tank, where suspended solids settle at the bottom of the tank to form primary sludge. For secondary treatment, the clarified effluent from the primary treatment enters the aeration tank, which is a biological treatment unit where oxygen is supplied to promote the growth of microorganisms. These microorganisms degrade dissolved organic matter in the wastewater through the activated sludge process. The mixed liquor is then conveyed to the secondary sedimentation tank, where biological flux settle as secondary sludge. A portion of the sludge is recycled back to the aeration tank, while excess sludge is withdrawn for further treatment. In this project, Microsoft Excel was used to perform all design calculation for each unit operation, including the sewer system, screening unit, grid chamber, balancing tank, aeration tank, and sedimentation tank. Meanwhile, AutoCAD was utilized to produce layout drawings and plan schematics to clearly illustrate the wastewater treatment process flow and the arrangement of the treatment units.
For this section, I will explain the design population equivalent or PE for the purpose housing scheme. Based on MSIG standard, the total design capacity has been calculated as 7,443 population equivalent. The PE is determined by considering all facilities within the area, not only residential houses. The largest contributor is the 800 semi-detached houses, which contribute 4,000 PE, followed by fully residential occupant with 2,000 PE. Other facilities such as school, market, restaurant, mosque, petrol pump, laundry, public toilet, bus terminal, and recreational park are also included. Each facility is calculated using the recommended PE conversion factor, such as PE per houses, per student, per stall, or per area. After summing up all contribution from residential and non-residential activities, the total population equivalent is 7,443 PE. This value will be used as the basis for the design and sizing of the wastewater treatment system to ensure it can operate safely and efficiently. This part explains the sewer system design. The sewer system is designed to convey wastewater efficiently to the treatment plant while maintaining self-cleaning velocity. This is important to prevent sedimentation and blockage in the sewer. Based on the design calculation, the sewer is designed to operate at 70% full flow, or D over D equals to 0.7, to accommodate peak flow condition. Referring to Table 3, the design is based on a population equivalent of 7,443. The peak flow is 0.073 cubic meter per second, while the minimum flow is 0.005 cubic meter per second, which is checked to ensure safe cleaning condition. The full flow capacity of the sewer is 0.086 cubic meter per second, calculated using the Manning formula with a Manning coefficient of 0.012 for concrete pipes. A slope of 0.01 or 1 in 100 is selected to maintain acceptable flow velocity and avoid erosion. For the sewer dimension shown in Table 4, the pipe has a width of 0.28 meters and a flow depth of 0.196 meters under the design condition. Overall, this design ensures the sewer operates safely and efficiently under both minimum and maximum flow conditions.
The pump station is designed to temporarily store and leave wastewater to downstream treatment units, ensuring a stable and continuous flow throughout the system. The design is based on a population equivalent of 7,443 and a peak flow rate of 6,311.55 cubic meter per day, which is equivalent to 0.073 cubic meter per second. A retention time of 30 minutes is applied as a standard holding period to prevent flow surge and ensure smooth operation. This results in a required storage volume of approximately 131.49 cubic meters. The pump station is designed with a compact layout using a 1:1 length to width ratio, with dimension of 8.11 meter by 8.11 meters and water depth of 2 meters. Overall, the pump station design is adequate to handle peak flow conditions while maintaining efficient and reliable wastewater conveyance to the treatment.
Primary screening. Referring to the table, the primary screening design is based on a population equivalent of 7,443 with a peak flow rate of 0.073 cubic meter per second. Primary screening. Referring to the table, the primary screening design is based on a population equivalent of 7,443 with a peak flow rate of 0.073 cubic meter per second. The selected design velocity is 0.9 meter per second. The screen uses 8 blades and a blade thickness of 10 ml and a clear opening size of 50 ml. The screening chamber is designed with a width of 0.2 meter and a depth of 0.7 meter, meeting the design requirement.
In this section, I will explain the secondary screening design parameters. The design is based on a population equivalent of 7,443, which is consistent with the overall system capacity. The peak flow rate used for the design is 0.073 cubic meters per second. A design velocity of 0.7 meters per second is selected to ensure effective screening while preventing clogging and excessive head loss. For the screen details, the blade thickness is 5 mm and the opening size between blade is 15 mm. These values are chosen to allow wastewater to pass through while retaining large solids. The system used 14 sets of blades calculated based on the total screen width and the combined blade and opening size. Referring to the screening dimension, the theoretical width of screen is approximately 0.9 meters with a length of 0.28 meters and a water depth of 0.5 meters. Overall, this secondary screening design ensures efficient removal of solid while maintaining smooth and stable flow into the next treatment process.
The grid and grease chamber was designed for a population equivalent of 7,443 with a peak flow rate of 0.073 cubic meters per second. The selected detention time is 6 minutes, equivalent to 360 seconds. So based on this detention time, the required tank volume is 26.28 cubic meters with a total air requirement of 1.08 cubic meters. The chamber dimensions are 3.6 meters in width, 4.0 meters in length, and 2.0 meters in depth. The balancing tank was designed for a population equivalent of 7,443 with a peak flow rate of 0.073 cubic meters per second. The selected retention time is 1.5 hours based on MSIG volume 4. Using this retention time, the calculated tank volume is 394 cubic meters. The tank is designed with a width of 7 meters, a length of 20 meters, and a depth of 3 meters, providing sufficient capacity for flow equalization.
For the primary sedimentation tank, the peak flow rate is 0.073 cubic meter per second is used. The detention time is selected as 2 hours, which is equivalent to 7,200 seconds. Using this detention time, the required total surface area is calculated as 252 square meter. The system consists of 4 tanks, giving 63 square meter per tank. Each tank is designed with a width of 4.6 meter, a length of 13.8 meter, and a depth of 2.5 meter, resulting in a volume of 159 cubic meter per tank.
The aeration tank was designed using the activated sludge process because it is effective and commonly used for treating domestic wastewater with high BOD. The design flow rate of 1,674.68 meter cubic per day represent average daily conditions in the study area. A detention time of 5.71 hours and an F to M ratio of 0.35 were selected based on standard design guidelines to ensure efficient biological treatment and stable microorganism activity. The MLSS concentration of 3,000 mg per liter supports effective organic removal. The system used 2 aeration tanks to provide operational flexibility and allow continuous treatment during maintenance. Overall, this design is suitable, efficient, and capable of producing good quality effluent For environmental discharge,
This section explains the secondary sedimentation tank design. The design is based on population equivalent of 7,453 PE, which matches the overall treatment capacity. The calculated peak flow for the system is 0.073 cubic meters per second, and a standard retention time of 3 hours was adopted. Based on these values, the total sludge tank volume required is 788.4 cubic meters. To ensure the plant can continue running even during maintenance, two tanks provide the operational redundancy. Next, the performance criteria were checked. The surface overflow rate is 13.68 meter cubic per square meter per day, which is below the limit of 30, so it is acceptable. The solid loading rate is 41.04 kilograms per square meter per day, below the limit of 150, and their loading rate is 157.32 meter cubic per square meter per day, below the limit of 180. Therefore, all design criteria are satisfied. In terms of physical dimension, each tank has a width of 11.5 meters, a length of 40.12 meters, and a depth of 3 meters. This provides a total surface area of 461.38 square meters and a total working volume of 1,384.14 cubic meters. Overall, the secondary sedimentation tank design meets hydraulic and operational requirements, ensuring effective solid, settling and stable performance for downstream treatment process. Next, I will move into the discussion section of this project. In this part, I will explain the reasoning behind the design choices, the performance consideration, and the compliance aspect related to the system. This discussion highlights how the design supports both technical and environmental objectives. The sewer system uses reinforced concrete pipe because they are strong, durable, and suitable for long-term sewage application. They can withstand soil pressure and constant wastewater flow, especially in high population areas. The manning coefficients selected reflect realistic pipe roughness, ensuring smooth flow and reducing the risk of sediment build-up, blockage, and or low-velocity issues in gravity sewer. The designs complies with MS 1228, MSIG by SPAN, and structural requirement from BS 8007 were applicable. This confirmed the system is safe and suitable for the study area. Functionally, the selected pipe diameter and flow behavior allow wastewater to be transported effectively during both normal and peak condition, reducing risk surcharge or overflow. Environmentally, a proper sewer system prevents leakage and protects soil, water, and public health. Overall, the sewer design is technically sound and appropriate for domestic wastewater.
the pump station is included in the wastewater treatment system to ensure continuous wastewater flow in areas where gravity flow is not sufficient, especially in flat urban areas. It helps transfer wastewater to the treatment plant at a controlled rate, preventing high velocities that could damage pipes or affect downstream treatment units. The selected pump station also provides a storage volume that acts as a buffer during peak flow conditions, helping to stabilize variations in wastewater flow. The use of 4 tanks increases system reliability, as the system can continue operating during maintenance or partial failure. From the operational and environmental perspective, the pump station reduces the risk of untreated wastewater discharge by maintaining smooth and controlled flow. Overall, the selected pump station design is suitable, reliable, and effective for the
Primary
wastewater
screening is
treatment.
used to remove large and coarse materials such as plastic, paper, and household debris from domestic wastewater. Removing this material at an early stage helps prevent clogging, equipment damage, and operational disruption in downstream treatment unit. The screening system is designed with suitable opening size, velocity, and screen depth to ensure effective solid removal without causing excessive head loss or risk. Overall, effective primary screening improves the reliability and efficiency of subsequent treatment processes and support stable wastewater treatment plant operation.
Next is secondary screening. Secondary screening was ended to remove fine solids that are not captured during primary screening. Domestic wastewater contains small particles like food waste, plastic, and fiber that can pass through coarse screen and cause problems to downstream units such as pump and biological treatment processes. By removing this solid early, the system reduces load and later units, improve efficiency, and follow standard wastewater treatment practices. The selected configuration suits the domestic characteristic of the study area and maintains a balance between removal performance and acceptable head loss. Operationally and environmentally, secondary screening help reduce clogging, equipment damage, and pollution risk, leading to better treatment performance and effluent quality.
The grid and grease chamber is used as a preliminary treatment unit to protect downstream treatment, processes, and equipment. Domestic wastewater contains inorganic material such as sand and grit, as well as oil and grease from kitchen and household activities. If these materials are not removed early, they can cause abrasion, clogging, and reduce efficiency in pump and aeration tank. The chamber is designed with an appropriate detention time that allows heavy particles to settle while lighter materials like oil and grease float for easy removal. A detention time of 6 minutes was selected, which is within recommended standards for effective grit removal without allowing organic matter to settle. The chamber size and the use of air assist in efficient grit and grit separation, especially during peak flow conditions, from an operational perspective, this design reduces maintenance needs and prolongs equipment lifespan. Environmentally, it helps improve effluent quality and supports stable biological treatment. Therefore, the selected grid and grease chamber design is suitable and effective for domestic wastewater treatment.
The
in the
balancing
study area.
tank is designed to manage fluctuation in wastewater flow rate and pollutant load commonly found in domestic wastewater system. Variation between peak and low flow condition can affect the performance of downstream treatment unit if low equalization is not provided. By temporarily storing excess wastewater and releasing it gradually, the balancing tank protects biological treatment processes from hydraulic surges and short load. Mixing and aeration prevent solid settlement and maintain uniform wastewater characteristic, improving overall treatment efficiency and effluent quality. Next is primary sedimentation tank. The primary sedimentation tank is designed to remove suspended solid and reduce organic load in domestic wastewater before secondary treatment. Suitable solid and floatable materials such as oil, fat, and grease are separated at this stage to improve the overall efficiency of the treatment system. The selected detention time and tank design allow effective settling of heavier solid while preventing resuspension. This reduces the solid and organic load transferred to downstream biological treatment unit, improving their performance and contributing to better effluent quality.
The aeration tank with the activated sludge process was chosen because it is one of the most efficient and widely used method for domestic wastewater treatment. It is ideal for removing biodegradable organic matter and suspended solid due to the high BOD levels in domestic wastewater. Oxygen is supplied in the tank to support aerobic microorganisms which break down pollutants, producing effluent that meets environmental discharge standard. The hydraulic retention time of 5.71 hours ensures sufficient contact for treatment. Dividing the tank into two units increases reliability and flexibility, allowing continuous operating during maintenance. The sludge age of 6 days maintains a balanced microbial population and effective BOD removal without excess sludge. Environmentally, this process reduces organic pollution and prevents oxygen depletion in water bodies. Overall, the proposed aeration tank design is technically sound, environmentally friendly, and effective for domestic wastewater treatment in the study
Next
area.
was secondary sedimentation tank. Secondary sedimentation tank is important for separating sludge and producing clear effluents. Without proper settling, sludge and microorganisms would escape into the effluent. The design handles both dry and peak flow by providing enough surface area and stable flow condition for effective settling. Sludge return maintain active microorganism for treatment, while excess sludge removal prevent bulking. Overall, secondary sedimentation reduce suspended solid and protect the environment, making it suitable for the study area.
Discussion. This wastewater treatment plant is designed in accordance with the Malaysian Sewerage Industry Guideline NMS 1228 and it is suitable for treating domestic wastewater from residential areas. The treatment units are arranged in a systematic sequence to ensure progressive and efficient pollutant removal. Preliminary and primary treatment processes remove large solid, grit and grease, helping to protect downstream unit and maintain stable operation. The activated sludge process in the aeration tank effectively reduce organic pollutants such as BOD and COD. Finally, secondary sedimentation separate remaining solid, producing a clean, stable and environmentally safe effluent that meet regulatory requirements.
This slide presents the entrepreneurial opportunities that can be developed based on our wastewater treatment plant design. The proposed wastewater treatment plant is not only an environmental protection system but also a platform for sustainable and environmentally driven business opportunities. In this design, sludge is generated from both the primary sedimentation tank and the secondary sedimentation tank. Instead of treating sludge as waste, it can be further processed into value-added products such as organic fertilizer or soil conditioner. This creates a sludge-to-resource business opportunity, especially for agricultural and landscaping applications. Second, the treated effluent produced after secondary treatment has a quality suitable for non-potable reuse. Based on this design, treated wastewater can be reused for landscape irrigation, toilet flushing, and cleaning purpose. This provides opportunities for reclaimed water reuse service while reducing freshwater demand. Another opportunity is the development of modular wastewater treatment plant system based on this design. The wastewater treatment plant layout can be adapted into smaller scale or decentralized system for residential areas, institution, and hospital. This opens business opportunities in system design, installation, and commissioning. Wastewater treatment plants require continuous operation and proper maintenance to ensure consistent performance. Operation and maintenance service can be offered to manage daily operations, monitor system performance, and ensure compliance with environmental regulations. This creates a long-term service-based business opportunity. The final entrepreneurial opportunity is environmental consultancy and sustainable-based service. Expertise gained from this wastewater treatment plant design can be applied in environmental impact assessment, wastewater management planning, and sustainability consulting. Training programs and environmental awareness initiative can also be offered to industry, institution, and local authorities. This opportunity supports environmental protection while promoting sustainable development. In conclusion, the proposed wastewater treatment plant design demonstrates that environmental engineering solution can generate multiple entrepreneurial opportunities. By integrating resource recovery, water reuse, technical service, and environmental consultancy, the wastewater treatment plant design supports both environmental sustainability and economic growth.
In conclusion, this project successfully designed an integrated wastewater treatment plant for Taman Kubang Kerian, Kota Baru, with a design capacity of 7,443 population equivalent. The proposed WWTP is suitable to cater for current and future wastewater generated from residential, commercial, institutional, and healthcare developments in the area. The treatment system was designed in accordance with MSIG guidelines and standard wastewater engineering practice. It incorporates primary and secondary treatment processes that effectively remove suspended solid, organic matter, and pollutants, ensuring the protection of public health and the environment. The sewer network, pump station, and preliminary treatment units were designed to ensure smooth wastewater conveyance and to protect downstream treatment processes. The balancing tank stabilizes flow variations, while the primary sedimentation, aeration, and secondary sedimentation tank works together to achieve efficient biological treatment and clear effluent quality. Overall, the proposed wastewater treatment plant design is technically sound, environmentally sustainable, and operationally reliable. With proper operation and maintenance, this system can support long-term urban and institutional development while minimizing environmental pollution and health